So, now what we will do is we will try and look at simplifying this general expression to some specific cases. What we know is that z gamma is gamma naught exponent minus kappa x is valid for any potential as long as the electrolyte is z is to z, right. Now, so we know that this expression should can be simplified to psi is equal to psi naught exponent minus kappa x, of course, for the case of low potential, right. So, let us look at how do we do that. So, that is the Gouy Chapman solution, okay, and we know that gamma is exponent of z e psi divided by 2 k b t minus 1 divided by exponent of z e psi divided by 2 k b t plus 1, right. That is what that is a gamma naught, that is a gamma, right. That is what was here, right. So, that is what is here. Now, if we assume the low potential case, so what I can what one could do is this exponent term I can write as a I can neglect the higher order term and I can write exponent of z e psi divided by 2 k b t as z e psi divided by 2 k b t plus 1, and I am going to neglect all the higher order terms. Okay. Similarly, denominator also the same thing, I am going to only retain the first two terms in the series expansion of exponent of z e psi divided by 2 k b t. So, therefore, gamma becomes, so I can cancel these two. In the numerator I have z e psi divided by 2 k b t divided by, in the denominator I have z e psi divided by 2 k b t plus 2, because we are taking low potential case, okay, because we are taking low potential, we had so the low potential case is when z e psi divided by k b t is less than 1, okay, and because z e psi divided by k b t is less than 1 and that divided by 2 is going to be even further less than 1. Therefore, I can neglect this term. So, denominator essentially will be just 2. Therefore, gamma becomes z e psi divided by 4 k b t. I can do a similar simplification also for gamma naught as well, which again turns out to be z e psi naught divided by 4 k b t, and this gets cancelled, this gets cancelled, and you end up with the expression for the low potential limit. Okay. Therefore, the general Gouy Chapman solution simplifies to the Debye-Huckel approximation for the case of low potential. So, the other simplification one can do is that is a special case too. This is for large value of x, at which the potential has fallen to small values regardless of its initial potential. Now, we know that potential varies with distance, right. If you go away from the if this is psi naught is the initial potential, and as we go away from the charged surface, we know that the potential is going to decrease. Now, if we take some distance, okay, that is x, such that it is very large, that the potential has fallen to a very low value regardless of this initial potential. So, in such a case, what I can do is I can simplify gamma as z e psi divided by 4 k b t, because again I can invoke the condition that at a very large separation distance the potential is low. I can again only consider the first two terms, neglect the higher order terms. So, therefore, gamma becomes Z E psi divided by 4 kBt. However, because psi could be larger, psi could be any potential, therefore, I will have to continue to retain gamma naught as it is, because I can't invoke the low potential case like we did for the earlier case, because now gamma could be gamma naught could be significant, or gamma naught psi being could be any value. Therefore, I am going to retain gamma as gamma naught. Therefore, for the case where for a very large value of x such that the potential has fallen to a very small value regardless of the initial potential, I can simplify the Gouy Chapman theory to take the form Z E psi divided by 4 kBt, that is on the left hand side, and the right hand side remains the same. If you take the third special case, again this is for a very large value of x such that the potential has fallen to a low value. Therefore, the simplification that we have done in terms of writing gamma naught as Z E psi divided by 4 kBt will still hold, and on the right hand side you had gamma naught exponent minus kappa x. What you see here is a table where gamma naught is tabulated as a function of psi naught, that is psi naught in millivolts. This is gamma naught. If you look up this table, it turns out that if you look at very large values of psi naught, gamma naught essentially is very close to 1. Okay. Therefore, if the surface potential, okay, if the initial potential is very large, gamma naught will it is approximately equal to 1. Okay, that is from this table. Therefore, Z E psi divided by 4 kBt becomes exponent of minus kappa x itself, okay, because gamma naught is equal to 1. Therefore, from this I can write psi as 4 kBt divided by Z E into exponent of minus kappa x. Okay. So, these are the three simple special cases one could derive from starting with the Gouy Chapman theory. What is plotted here is potential in millivolts, and that is the separation distance. And if you look at this plot, there are 4 expressions. Okay, there are 4 lines, a continuous line, a dashed line, and dashed and dotted line. Okay, they are essentially they are essentially different solutions. That is the Debye-Huckel approximation. That is the Gouy Chapman theory, and this is for the case where the potential has fallen to a very low value regardless of the initial potential, and this is the case where the potential has fallen to a low value regardless of the initial potential, and the initial potential being very high. Okay. So, if you look at the solution that is plotted for specific case, psi naught is 77.1 millivolts. This is a significant potential. This is not the low potential, because we said that the potential has to be of the order of 25 millivolts for one to consider the potential to be the low potential case. So, therefore, psi naught is equal to 77.1 is not a low potential case, and kappa is given by this. So, kappa inverse is marked here, that is a kappa inverse corresponding to this kappa value, and this is the kappa value that you have is for a 0.1 molar solution of electrolyte. And so, the best expression that one could use to predict the variation of potential with separation distance in this particular case is going to be this expression, right, because this is the Gouy Chapman theory, which is valid for the symmetric electrolyte 1:1 in this case, and we know that it is applicable for any potential, because we are not invoking the low potential limit case. Therefore, this particular line, that is this line that I am tracing now, that is the solution that corresponds to the Gouy Chapman theory. But however, if you look at the other two line, okay, that is this line, okay, as well as this line, these are, one is for the low potential limit and the other one is for the case where the potential has fallen to a low value regardless of what is the initial potential. We know that these two also do a reasonably good job. That means though the potential is best described by the Gouy Chapman theory, that is this expression, okay, this as well as this still do a very good job of predicting what is the variation of potential with the separation distance. However, because of the fact that the potential that we have considered is 77.1 millivolts, okay, that means it is not significantly large to take gamma naught is equal to 1, as it is evident 63, the equation 68, that is the case corresponding to the special case for large value of x and large value of initial potential. It does not do a good job of predicting how the potential varies with separation distance. Therefore, depending upon the situation, you should be able to use one of these expressions to find out how the potential varies with separation distance. Now that we know how the potential varies with separation distance, we can also look at the variation of the concentration of co-ions and the counter ions as well, from in the vicinity of the charge surface. So we know how the potential varies with separation distance, but however, if we want to know how does the concentration of, in this case you have positively charged surface, therefore the negatively charged ions are going to be the counter ions. Of course, I could also have positively charged ions as well in the solution, which are going to be co-ions, and how does their concentration vary with separation distance is also of interest. Okay, so for that, what we are going to do is to again start with the Boltzmann factor. So we know that Ni divided by Ni infinity is exponent of minus Zi E psi divided by kBt, and this Ni is not a constant, right, and Ni infinity is fixed by the concentration of the electrolyte in the solution. That is a fixed quantity for a given concentration, and this is a constant, okay, this as well, and Zi is the valency of the ions, right. So once that is fixed, so everything is a constant here except for psi, and Ni varies with separation distance. We know that psi also varies with separation distance. Now, because we have derived how does psi depend on varies with separation distance, we can substitute a relevant expression for psi. So if I assume the low potential case, I can replace psi to be psi naught exponent of minus kappa x. Therefore, now that I know how psi varies with separation distance, I should be able to also calculate how does the concentration of the ion varies with separation distance. So therefore, from this approach, I can actually calculate what is the concentration of the counter ions and what is the concentration of the co-ions. In this case, both of them are scaled with N infinity, which is the concentration of the electrolyte that I have in the solution, and how does the concentration of the counter ion decreases as you go away from the separation distance, and how does the concentration of the co-ions again varies with separation distance. One could calculate from this approach. what would also be interest would be what is called as the distribution of excess ion concentration, that will be given by n minus n plus, that is the difference in the concentration of the co-ions and the counter ions, and how does that vary with separation distance. One should be able to calculate all of this from the simple formulations.